On the screen is a decision analysis problem. We have a decision alternative 1, decision alternative 2, and decision alternative 3. I sent all you guys this. Now you have a state of nature 1, state of nature 2. I say, what is the expected value without perfect information if P is 65? Show your answer using both the graph and the table. Explain the best you can. Now, from this scenario, to get expected value without perfect information, you could just go ahead and say, what is the best expected value when you multiply across. Now, I'm going to look at the answer key that I worked out, and then we'll figure it out from there. So, you look at this, and you have the answer. Well, to find the answer first, I wanted you to do it in both the graph form and the table. So we'll start with the graph, the more difficult of the two. So we have decision alternative 1 is 40 and negative 10 for respective state of nature 1 and state of nature 2. So I put that in the slope-intercept form, such as 40p minus 10 times 1 minus p. You get 40p minus 10 plus 10p, because a negative and a negative will give you a positive, and you get 50p minus 10. You go on to decision alternative 2, and you do the same thing again. Decision alternative 3 will just give you 0, because it's 0 on both sides. So I went ahead and graphed it. And the way how Dr. Schindlerbeck graphs it is that she gives you where p is 0 and p is 1, because those are the two extreme points, and you take it from there. Oh, look. We have someone. Miss Shani. Alright. We got a customer. Alright, so before you arrive, I was just explaining to the camera that I asked you a simple question. What is the expected value without perfect information if P is 65? Well, it should be P is 0.65. Not 65, but 0.65. So I said, show your answer using both the graph and the table. Explain the best you can. And then so we look at the table, and we have decision alternative 1, 2, and 3. Decision alternative 1 for state of nature 1 is 40. For state of nature 2 is negative 10. Decision alternative 2 for state of nature 1 is negative 20. And the third one, and state of nature 2 is 30. Decision alternative 3 is 0, 0. So my question is, what is the expected value without perfect information if P is 0.65? So I went ahead and did it, and I will explain to you as we go along. So first off, there were a couple things I needed to do. The first thing is, if I'm going to graph it like the professor has it, I have to make sure that I have the slope for each one. So that's the very first step. I have to find the slope for the 3 lines. So I said, okay, decision alternative 1. P is in 40 is in the P column, and negative 10 is the 1 minus P column. So you expand the brackets. 40 times P minus 10 times 1 minus P. 40P minus 10 plus 10P, because a negative 10 and a negative P gives you a positive 10P. Then you group like terms, you get 50P minus 10. And I did the same thing for decision alternative 2. Negative 20 and 1 minus P, and you assign them negative 20P plus 30 minus 30P. This is 30 times 1 and 30 times negative P. And then you group like terms, and I get 30 minus 50p, or if you want to keep the p in front, negative 50p plus 30. So you with me so far? Okay. For decision alternative 3, I never really did anything because it's 0 on both sides, so it's just going to equal 0. Now, let me go back to opening up the problem. Okay, so with graphing it, do you remember how Dr. Schindlerbeck graphs it? Like, she does something with the p-values to make sure that you can graph it properly. Do you know what she does? Okay. So you're in the online class. Okay. So what happened is, with the p, to make sure you can accurately well, I wouldn't say 100% accurately, but more than likely get the correct graph, she chooses the two extreme points, right? So what do you think the two extreme points for a probability is? Extreme points means the lowest it can go and the highest it can go. So what are the two extreme points you think there is for a probability? Yeah, in general, what are the extreme points for a probability? The lowest a probability can go and the highest a probability can go. Well, 0 to 100%, but convert that to probabilities. Convert that to a decimal, it would be from 0 to 1. But you're right, it's from 0 to 100, which is absolutely correct, but she just converts it from 0 to 1. We want to keep it as decimals. So she comes down, well, I came down, and what you do to graph this accurately, you let P be 0 and P be 1, and you solve for Y. In this case, P is your X value. And as you can see, P goes from 0 to 1 on the graph. So we go P is equal to 0, what should Y be? And we just plug it in back into our slope up top. And we say, okay, if P is 0, Y is negative 10. Because it's 50 times 0 I have here, minus 10 gives us negative 10. And if P is 1, it's going to be 40 because it's 50 times 1 minus 10. The blue line is my decision alternative 1. So you see negative 10, which is 0, negative 10, and then third, and then 40. I know this is like a little off, but it's 40 and 1. Yeah, 1 comma 40. And I did the same thing for decision alternative 2. If decision alternative 2, if the P is 0, what should Y be? When we come up here, negative 50 times 0 gives us 0 plus 30. That will give us 30 for Y. And then if we have Y, if we have P equals 1, it's going to be negative 20 because negative 50 plus 30 gives us negative 20. So I graph it, right? The next step is I said P should be 0.65, but generally you want to choose from 0 to 1, and you graph those points, as I mentioned earlier. And then we said if P was 0.65, what's your expected value? Or what decision would you make when you go on to explain? So we draw it. However, we don't know where they intersect, so I cannot tell you if we're going to be using decision 1 or decision 2. This 0.4 is where they intersect, and I go on to solve it on the next page. So what we do is that we set D1 equal to D2. We set the two slopes equal to each other to find when they intersect. So 50p minus 10 equals 30 minus 50p. We do simple algebra, and you come out to get p is 0.4. This is the indifference point. When p is equal to 0.4, it doesn't matter if you go with decision 1 or decision 2. And then based on that, I'm able to do a graph and label it correctly. Now what this is saying up top is say when p is between 0 and 0.4, the best decision to make is decision alternative 2. Because you yield a higher payoff than decision alternative 1 or decision alternative 3, which is doing nothing. So then you say between 0 and 0.4, you go with decision alternative 2. Between 0.4 and 1, you now go with decision alternative 1. Well, the question said what is the expected value of 0.65? Well, expected value, you're looking for a number. Well, to support your answer, you look at the graph and you say, okay, if it's 0.65, that means that it's between 0.4 and 1. So we should get decision 1 as what the option we will be choosing. However, we need to find the expected value of decision 1 at 0.65. So you go back to the table, you let P be 0.65 and 1 minus P is 0.35. You do the according math. So 40 times 0.65 plus negative 10 times 0.35 gives you 26 minus 0.35, 23.5. You do it again for decision alternative 2, and you get negative 2.5. This is the expected value without perfect information, because it's the higher of the two, of 23.5, decision 1 is higher. And how do you explain? Well, you use the graph as your supporting information, saying, okay, since it's 0.65, it should be decision alternative 1. Let's double check by finding the actual values. When we find the actual values of 23.5, we get to see that, A, it is indeed correct because decision alternative 1 is the better of the two choices. We just answered probably 2 or 3 questions, and then multiple questions can be asked from this problem. So you could go ahead and say, okay, what is the decision alternative if P is now 0.20? You look at the graph, or you can plug in P being 0.20 back into the table and take it from there. She could say, hey, what are the best times to go with decision alternative 2? And you could say if P is between 0 and 0.4, it's best to go with decision alternative 2. But this is a structure of decision analysis or sensitivity analysis, however you want to talk about it. And this will allow you to answer any questions given to you from here. Min-max, regret, and maxi-max and maxi-min we went over already. This is the second part that you will get questions and information from the table. And I may have asked just one question, but that question relied on the explaining, and I'm saying, hey, use things to support your answer, and then if you can properly understand how to support your answer, you should be able to do this problem no matter what numbers are thrown at you. So if you look again, step 1, find the slopes of each of the lines, graph them using the two extreme points, 0 and 1, find the indifference points. Now, there may be times where D1 and D2 intersect below the x-axis, and so you don't want to find that because you don't want to be in the red, so you'd probably just find where they intersect with D3, which is do nothing. You set them equal to each other, and you take it from there. And then you find the indifference point, and then you can solve whatever questions they say. Now, it could happen where they say, if P is 0.4, what decision would you make? Well, there's a reason why it's indifference. You could say, hey, we could go with D1 or D2. It doesn't matter because they both will yield the same result at 0.4. Now, this is the point I would like to ask questions, but since there are no one is here, I'm going to, I guess, say take a 10-minute walk-around break and come back. If there's no one here still, I'll just wait till 5 to go over decision tree. This thing, fairly simple. Create a problem, go through it. Let me pull it back to actual problem. That was the question. It should have been 0.65 instead of 65. Show your answer using both the graph and the table. Explain the best you can. This is a great exercise to help you understand how to do this. And then I'm going to end up using this very same table, creating it into a decision tree, and then asking maybe 4 to 5 questions on decision tree. And that as well will be very interesting. We're doing over sensitivity analysis, how to look at the problem, how to answer the question, how to graph it, how to get the slope, and everything. So I think I'll be back at 5 to go over the second part, which is to deal with the decision tree. Give you a preview of what to expect. This. This. Yep, this is what we're going to be looking at, the decision tree. What does this all mean? How to answer those 4 questions effectively. Yeah. So, I'll be back in at 5 to take a crack at this. Alright guys, have a nice day.